All right, let's get into it. Today, we're going to put on our detective hats because we're about to solve a mathematical mystery.
So have you ever thought about it? In all those great detective stories, everything kicks off with just one single, really important clue. Our job? It's to figure out what that clue is really telling us and who, or, in our case, what number, is behind it all. And here it is, our first case file. The clue reads, n plus 3 equals 7. Now this statement, it's kind of incomplete, right? It's open, because we don't know the identity of our mystery variable n. Is the clue true? Is it false? We just can't know. At least, not yet. To put it simply, an open sentence is just a statement with a placeholder, a variable. And whether it's true or not depends completely on what value we decide to plug into that spot. This right here, this is the heart of our entire investigation. Every good detective needs a lineup of suspects. We can't just go around accusing every number out there. So we got to narrow down the field to a small, manageable group of numbers we're interested in.
So, in algebra, this list of suspects has a name. It's called the domain, or sometimes the replacement set. For this particular case, our domain is super specific, just 5 numbers, 1, 2, 3, 4, and 5. Our culprit has to be on this list somewhere.
Okay, it's time. Let's bring them in one by one for a little chat in the interrogation room. We're going to take each suspect from our domain and see if their story checks out by substituting them for n in our clue.
First up, the number 1. If we pop a 1 in for n, we get 1 plus 3 equals 7. Well, that just means 4 equals 7. Yeah, that's definitely false. Okay, suspect number 1 is cleared. You're free to go. Next up, suspect number 2. Let's see. 2 plus 3 equals 7. Nope, that's false too. Innocent.
And what about number 3? 3 plus 3 equals 7. Also false. Man, we're kind of running out of suspects here. Who could it be?
All right, bring in number 4. Let's try this one. If n is 4, then 4 plus 3 equals 7. Hold on a second. 7 equals 7. Hey, that's a true statement. We've got a match. The clue finally makes sense.
And there we have it. The number 4 is the only value from our whole list of suspects that makes our open sentence true. Case closed, we found our culprit.
So in detective terms, we've found the guy, but in math terms, we've found the solution set. Think of it like the official file that has all the values from the domain that solve the mystery. In this case, it's a pretty exclusive club with just one member, the number 4.
But, not all cases are that simple. Sometimes you don't just have one culprit. Let's take on a new case where things get a little more complicated.
Okay, here's the new file. This time, our clue is an inequality. 2 times n is greater than 3. And our lineup of suspects is changed too. The domain this time is 0, 1, 2, and 3. So the question's the same. Who from this list makes our clue a true statement?
So let's run through the interrogations real quick. If n is 0 or 1, the statement is totally false. But check out what happens next. If n is 2, we get 4 is greater than 3. That's true. And if n is 3, we get 6 is greater than 3. Hey, that's also true. Whoa, hold on a minute. We don't just have one match this time, we've got 2. Looks like this wasn't the work of just a single number. And this just goes to show you that a solution set isn't always limited to a single member. In this case, both 2 and 3 make the open sentence true. So our solution set is 2, 3. We had multiple culprits. But what happens when you bring in all the suspects? You question every single one, and none of their stories check out. What do you do when a case seems to have no culprit at all? Let's take a look at this next case. The clue is y plus 5 equals 9, and our domain is tiny, just the numbers 1, 2, and 3. So we test 1. 1 plus 5 equals 9. False. We test 2. 2 plus 5 equals 9. False again. We test 3. 3 plus 5 equals 9. Still false. We've gone through our entire suspect list. Uh-oh. We've got a problem here. Not a single one of our suspects makes the sentence true. It's like the crime wasn't committed by anyone we had on our list. Our culprit just isn't in the domain. When this happens, we say the solution set is the empty set. You might also hear it called the null set, and it's represented by this cool symbol, phi. It's really just the official way of saying, hey, based on the suspects we had, this case is unsolvable. So, after going through these investigations, you're basically equipped with the fundamental tools of a real math detective. Let's do a quick review of what's in your new toolkit.
Just remember this. The open sentence, that's your main clue. The domain is your list of suspects. The act of substitution, that's the interrogation process. The solution set is the official file identifying your culprit or culprits. And the empty set? Well, that's what you file when you have an unsolved case on your hands.
You see, the real takeaway here is that algebra can be a lot like a detective story. You get a clue, you get a list of suspects, and it's your job to find the truth. So really, the only question left to ask is, what mystery are you going to solve next?